I'm going to talk about a new work called Soup of Experts, Pretending Specialist Models with Parameter Averaging. And it's a joint work with my colleagues at Apple, Angelo, Skyler, and David. So we are going to play a game, okay? So let's try to play a game. It's very interactive. Okay, so the rules of the game are the following. You have a very large pre-training budget. So congrats, you have lots of time and lots of GPUs to pre-train a model. So you can spend maybe months pre-training a model. So that's great. And now, after that time, so you have a very long time to pre-train a model. And then, after, let's say, 1 month, I will come to you with a very small data set. And I have this data set, and it's like a very precious data set to me. It may be the cooking recipes of my grandma or something very precious. And so it has two different things. The first thing is that it's very small, so I have very little data in this data set. And also it's very precious to me, so I want to have a very good model on this data set. And now the game is the following. So I had this month to prepare, and then after a month, I receive a data set. I have never seen this data set before, and I have to get a very small model. So maybe like, just to give an order of magnitude, let's say we just want 100 million parameters, or maybe just 1 billion parameters. And we want this model to have a very good performance on this dataset that we have never seen before. So you have lots of time to prepare, but you have never seen the dataset before. And then I come to you, I give you a dataset, and now you have like maybe a minute or two to give me a model that is really good on, on that dataset, okay? So I will give you a bit of time to think about it and try to see if you can come up with a method to do that. And so the goal of my talk is to explain the method to answer this question. So I will, while you think about it, I will keep on going with my presentation. So, of course, to solve this problem, we have two issues. So the first one is that I have a very strong constraint on the size. So I need to have a small model, and that means that I cannot do the usual paradigm of just taking the whole of internet and training my small model on this one, on this data set, because my model is small, so it has to do trade-offs. It has to allocate its capacity to do some things, and if it allocates its capacity to do one task, it cannot do another task as well, because it has a very little number of parameters. And so that means that if I do my usual pre-training recipe, I will never get a good specialist. So this method will most likely not be very efficient. And then the other issue is that I don't have time. Okay, so I get this data set, and I cannot train a model on it because it's too small, and I don't even have time to do so. Maybe I don't even have a GPU, or it's gonna be very complicated. But I have lots of time to prepare. Okay, so to answer this problem, the first answer is that we have, as usual, not only one pre-training domain, but we have multiple. So we have a collection of pre-training domains. So I'm going to call them D1 to DK, and these are different data sources. Okay, so each one can be a different textual domains, for instance, if we train language models. And we have lots of samples in each of those domains. Let's say that for the sake of this talk that we have infinitely many samples in those. And so we can query samples from each of those domains. And that means that I can sample from what we call a mixture. Okay, and a mixture is very simple. You give me a probability vector H that I'm going to call a domain weight. It's a vector of size K. And then I can sample from the corresponding mixture. That means that I will sample from the domain I with probability Hi. And so if Hi is a large number, I will sample a lot from domain I. And if Hi is small, I will sample a little bit from that domain. And so that's an illustration. Here it's just a mixture of domains. And this is what everybody does when they pre-train models, actually. And so the idea is that now I can train a model for any given mixture. So if you give me a domain weights vector H, I can pre-train a model that will be good for that mixture by just minimizing, as usual, the empirical loss over that mixture. And of course, if I take a different mixture H, I get to a very different model. The model I get is very dependent on the mixture. And so before I go ahead, I need to talk to you about a method called CRISP that we presented actually yesterday at the conference, and that's the basic idea for what I'm going to talk about. And so the idea is to use importance sampling. So the idea is super simple, and it solves part of the issue. So if you come to me with a very small data set that is very precious, that has very little bit of data, the idea is super simple. I'm going to do two things. I'm going to first try to find a histogram or a domain weight H that approximate my specialist set. So the idea is that I try to find an histogram H such that my specialist set resembles the mixture corresponding to H. So that's, we have methods to do that. It's actually pretty simple. And then the idea is that we train then a model using that histogram. And that means that we have two things. We are going to train on data that looks like my specialist data. And we also have a lot of data because these are data coming from my training domain. So I have these two things. And then I get to a model that will hopefully be very good on my specialization data set. Now, of course, this method does not solve the problem that I mentioned before, because you have to know the specialist set before you do your pre-training. Your pre-training is, okay, I'm going to sample according to this mixture, but you need to know what the mixture is, and that means that you need to know beforehand what is the specialist set. And so that does not answer the question I was asking you. And so the idea actually is very simple, is to combine this idea of crisp with what people call in optimization, amortization. So amortization is a very simple concept. The idea is that basically what we want to do when we train a model is that you have an histogram H and you want to minimize this loss that depends on H. And so amortization is the idea that these problems, even though they are not the same, they share a common structure. They are very similar. If you move H a bit, you're going to have a problem that is quite similar. And so we are going to try to amortize. And so amortization is the following concept. So it's when you have similar instances of the same problem that are repeated. And here, one problem is pre-training a model with an histogram H. And amortization is going to try to predict what is the solution to that problem with respect, as a function of H. And so trying to predict, without doing any optimization, what is the solution to that problem. And so now you can wonder, what am I doing at that workshop, right? So that's a very fair question. And so the answer is this. So we are going to also use ideas from model merging. And so this slide is going to be very obvious for most of the audience, but I'm still going to do it. So the idea is that we can combine models parameters linearly. And so with respect to the framework I was mentioning about, before, the idea is the following. So if you take a pre-trained model theta that you got, that's a pre-trained model, so it was trained for a long time, and then you take two different domain weights, H1 and H2. Then let's say that you start from theta, you fine-tune on the mixture corresponding to the first domain weights, and you get some weights theta 1. So those weights are obtained by fine-tuning on that mixture, so they are obtained by optimizing the loss with respect to H1. Now let's say you do the same thing, but with the other histogram H2, you get another set of weights theta 2, and then, as you all know, here, if you average those weights, they are going to be good both on H1 and on H2. So that's the basic idea of model merging. You can merge in more fancy ways, etc., but that's the main idea. And so the key insight that I'm going to use is that some models parameters can be linearly combined. That's obvious to all of you, but I think it's a very important message. And so what we propose to amortize this learning of optimization with respect to the mixture is the following architecture. It's what we call a soup of experts, because it's a bit like a model soup that we learn. And so the idea is the following. It's an architecture that is instantiated for any different histogram. So the idea is the following. You give me an histogram H, some domain weights H. I simply make them pass through an MLP. That's a very small MLP. It will give me n different scalar numbers, and n is usually like 100 or something. So this MLP is very small. And these numbers, I use them to form a linear combination of shared weights. So S are shared, so they do not depend on the histogram, and experts weights that depend. So all of these things here are banks of coefficients that are of exactly the same shape as the original model that you want to train. And basically what we do is very simple. We just take these shared parameters and then we do linear combination of all of these expert weights. So like we do in the model merging, but we have the coefficients of this linear combination that are a function of the input histogram. So if you give to a soup of expert a histogram, you pass the histogram through an MLP, you get coefficients, and then these coefficients are used to merge the parameters of the model. And then in the end, you get a single parameter theta that is of the same shape as the shared parameters or all of the expert parameters. Okay, so that's the architecture. And then n is the number of experts, and so it's a new model, and its parameters are S, the shared parameters, the experts weights, and the MLP's parameters. And we are going to learn all of those parameters jointly during pre-training. So how do we learn to do that? We have to do some kind of meta learning. So what we are going to do is that we are going to have a meta distribution a meta distribution pi, and it's a distribution that gives you random histograms. And so now that you have this distribution that gives you random histograms, what do you do to train? First, you sample domain weights. So you sample a random histogram from the distribution pi, and then you do two things. So you have an histogram H. You first are going to instantiate the soup of experts, as I mentioned before. So you take this histogram, pass it through an MLP, get all of the experts' weights, merge them, and then you get some parameters. And then on the other hand, so that's on the side of the model, and on the side of the data, you are going to take this histogram and sample following the law, this law. So here, H1 was large, so you're going to sample a lot of data from your first domain, a little bit of data from the second domain, etc. And that gives you a mini batch X. And now you have, on one hand, a model. On the other hand, you have a mini batch. So you can do what everybody does in machine learning. You merge these two things, you get a loss, and then you backprop for this. And that allows you to update the experts and the MLP's parameters. And now, my claim is that this answers actually the riddle that I gave you in the beginning. Because now, if I have a soup of experts that is pre-trained, and you come to me with a new specialization data set, I can do a very simple thing. I first try to find, just like I explained to you in the CRISP method, I try to find a histogram H that resembles this data set. So it's very easy to do and very quick. And now that I have this histogram, I can just pass it through the MLP. I get the weights, I combine these experts, and I merge. And this is actually a very cheap process, right? I just have to do a forward pass through an MLP and combine the weights. So it's very fast. I can do this on the CPU because it's just about merging models. You don't have to do any training, and it's fast. So for the experiment, so we used a generic pre-training set, Red Pajamas V2, and we used the clustering algorithm over embeddings to split it into 4,000 different domains. And then for the specialization sets, we use 16 different data sets from the pile, so GitHub, Wikipedia, etc. We use model sizes mainly of size 110 million, and we use 128 experts. We have different baselines. So the first baseline is the thing that everybody would do, which is generic pre-training. So you take a model of fixed size and you pre-train it on your uniform distribution. We compare it to CRISP, which trains one model for each of the specialization sets, and also to domain experts, which would train one model for each training domain. And these are the results. So we have many more in the paper, but basically what we want to see are curves that are below the baselines. And this is the average loss that you get on the 16 specialist sets. And you see that the soup of experts is, in terms of time, more efficient than all of the other methods. And you see that the plateau is much lower than that of generic pre-training. So you get a method that really helps you instantiate experts very easy. And thank you for your attention. Thanks.
Do you have any sense for how many experts you should be making, or like whether there's any sort of scaling laws for this?
Yeah, so that's a very fair point. So when you increase the number of experts, so the thing about the number of experts that is going to increase kind of the model capacity, but it's not going to increase the size of the final model you get. So that's another axis of scaling, and we actually have experience. So in our experience, we see that actually, do I have the curves? Yes, I do. So basically, these are the little. So don't pay attention just pay attention to the stars, and this is as a function of the number of experts. And so you see that this is the y-axis is the loss, and the x-axis is the kind of, if you want, the number of experts. And so you see that it decays and then it plateaus. And so the fact that it plateaus a bit is I think it's maybe an optimization issue. And so we could probably fix this issue. But basically, you see that it scales with the number of experts up to a point. So you have like kind of a kink so far. Having more experts help having better models while still having the exact same model size in the end if you want to ship a model.
So you have a little bit of data that you use to basically figure out the domain mixing weights, right?
Yes.
And do you have experiments where you basically try to adapt the combined model also on that little data? And if you do, one thing you could also use that little data for is to basically doing context learning with the larger model. Does that like as another baseline of like comparing against?
So there are two parts.
Yeah.
The first part is exactly yes. So that's a very good point. We also so if you have a bit of data and if you have a bit more time, so the idea is that this is fast. If you have, for instance, if you can afford to backprop, then you can learn the weights alpha 1 to alpha n that are minimizing the loss on your data. You just have 100 weights, so it will be pretty fast to do. But this is still costly because you have to backprop through the network. But that works fine. Actually, in our experiments, we found that you actually can, in most cases, you actually recover the ways that you would be using anyway. So that's a good point. And then about using this data to do in context learning, I think it's another baseline, of course, but I don't. That depends on. It might not be fair if you are under a model size constraint, and that's the case in. In our whole project, we say we want in the end to shape a model that has 100 million parameters, and then if you instead you try to use a 7B model, of course it's going to be better, but it doesn't fit the constraint, so we discard those models. They will be better, of course.
There are some works on like prompted language, like prompted pruning, where you can basically use the in context data to prune the model just from prompting. That's also like an interesting baseline to look into.
I was not aware of this. That's interesting. Thanks.